Hello, today we're going to look at Newton's second law. What we're going to do is we're going to apply a force on this coat. And when we apply a force, measure the acceleration. And using the acceleration, we're going to try to find the theoretical value of the mass. Now for part A, this coat has a mass of 0.213 kilograms. So we're going to try to find that experimentally. Once again, by applying a force, measuring the acceleration, and using the sum of forces is ma. F equals ma, Newton's second law. Now for this first part, everything is perfectly horizontal. And how we're going to apply a force is we're simply going to pull on this coat with this string. But we don't want to just pull arbitrarily. What we're going to do is we're going to put the string over this pulley and hang mass. If we have a mass hanging, we can say that the force due to gravity on this mass is mg. M in this case being the mass of this weight, g being the 9.8. And if I put it over the pulley, that is going to go and be the force in the horizontal direction. Which means when I put this here, when I let go, this is applying a force mg that way. Now, as you can see right now, this isn't moving, but I am on an air track. This whole thing is set up like an air hockey table. There's an air supply over there, I'll turn on in a second, and it will cause a frictionless surface. Right now, friction is keeping it from moving. And the last thing I want to point out are these two photo gates. So if you notice, the flag here has two teeth. What is going to happen is the photo gate is going to measure how long the first tooth goes in and how long the second tooth goes in, giving me two different distances for over time at each photo gate, which means at each photo gate I can measure a velocity. And if I measure the velocity at two different points and figure out the time in between, I can get an acceleration. And that's how we're going to get acceleration. Now I'm not going to show all the trials today like I didn't last time either. I will be giving you the data, but I just want you to see how it's run. So here's the general idea. Let me take off the mass first. And I'm going to turn on my air. And then once the air is on, I will apply my force. Once again, whoops, by just hanging this mass. And so I just let this go. And there you go, it accelerated through. I can get the acceleration right off this timer. And once I have that acceleration, I can figure out for this mass, what was the acceleration. I'll then repeat this for various masses. And we can make a graph of F versus A. That's only part A. I'll come back with part B in a second with another video. For part B, we're going to make this a little more complicated. We're going to turn this into the dreaded ramp problem. This thing is no longer level. Now, we're still going to apply the same forces here in X with the same weights. But now, because we're at a ramp, and this is kind of a small ramp, but if I go bigger, we're going to have a component of gravity putting it down the ramp. If I didn't have this mass here and I just let this go free, it's going to slide down the ramp every time. Which means we are going to have to deal with a component of gravity. So if you look at your data table, there is a thing for the force for this tension, but there's also a sum of forces in X. To be fair, there was one in part A also. In part A, all of the forces in X, the only force in X acting on it was this guy here. But now the forces in X is going to have two components, the force hanging and also the component of gravity. Now to find the component of gravity, you will need to know the angle. I will be giving you a way to calculate that angle. Actually, no, I'll just give you that angle directly. Sorry, I should probably plan these ahead of time and not just film as I go, but hey, you get the fun to see my workspace. Now, I want to give you a way to measure the angle. Well, I'm going to measure two different points, the height of here. And using SOHCAHTOA, I can then find the angle. Or you can find the angle. Then what we're going to do is, yes, same idea. We're going to apply mass and we're going to see this thing move. But here's the interesting point. If I just put this mass and let this go, we accelerated up the ramp. And that makes sense. Now in this case, we traditionally put the right as the positive direction, but I kind of set this up backwards and didn't realize it. So we're going to actually say that up the ramp is positive today. It will make sense later on. All the forces pulling up make positive, all the movement up is positive. See, the reason for that is when I have less mass, like so, I just decreased the mass on here, I might find that when I don't have any friction, without friction, I accelerate down the ramp. You're going to see some of my acceleration negatives are negative. The negative acceleration values meant it went down the ramp. Once again, assume all forces this way, all positive, and all accelerations this way, all positive. When you find your sum of forces term, you should see that some are negative and some are positive, depending on the value. Now, of note, when you find the component of gravity, you do need to know the mass of the cult, but we're solving for the mass of the cult. Kind of a weird thing. When solving for the component due to gravity, just assume the theoretical value of the cult, 0.213 kilograms. Other than that, make sure you look at the PowerPoint. It's really going to help you here. This is a little bit of a complicated one. Good luck.